He's Dan. I'm Josh. We have 3 minutes to talk repetition and recursion, so let's rock. When we need to do something many times, we can choose between iteration, such as loops, and recursion. So which should we choose and why? And it depends on how you think about a problem. Let's consider the problem of writing a factorial function as a quick case study. Whoops, there we go. So if we think of the definition of factorial, we might note that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is also 6 times 5 factorial. And if you look at it that way, then the general case emerges where n factorial is the same thing as n times n minus 1 factorial. It should have been in this slide, sorry about that. And the smallest examples we can come up with are 0 factorial and 1 factorial, both of which are 1. And when we look at it that way, the code almost writes itself. If we've got a situation where our n is 0 or 1, we just get a 1 back. And if we have something that's bigger than that, we take our number and multiply it by, n minus 1 factorial. And voila, we have recursion without really having to talk about the word recursion at all. Iteration is also good. Another way to go and set this up is to go and have a holder, such as the variable product here, which we initialize to the multiplicative identity. And then we grab all the numbers from 1 up to n, and we multiply that product by each of those numbers. And when we've done that, we're done. And so in this particular case, we have a for loop, which is a rather conventional thing, and that works great also. Just depends on how you approach the problem. We also have this bonus approach, this idea of a higher order function, which fits in the functional programming paradigm, doesn't involve assignment operators, much like the recursion example, and allows us to think abstractly all the way. So one way we could think about it is if we could just take all the numbers between 1 and n and reduce them by means of multiplication, we'd be done. And voila, we get this in one line. So there is, once again, another example of doing something over and over again, but we've got it abstracted away using this lovely function reduce. Okay. All these techniques are really useful, for a programmer to have in their cognitive toolkit, but they're not always created equal in the problem-solving process. For a brief discussion of that, here's the lovely Dan Garcia.
Thank you, Josh. So we realized, let's find a problem that's really beautiful, just elegant, just dripping with elegance to be written recursively, that's really hard iteratively. And so this is an example we came up with, which is how Josh, by the way, he should tell the story, on day 1 of his computer science class, he teaches the recursive tree. You've got to see that's a work of beauty to watch Josh do it. So this is the code on the right, is the code that they eventually write, and I added a delay so it slows it down, and it basically does what we call in computer science a depth first search. It goes down to the end, then backs up, and the thing about recursion is when you make a recursive call, you've got to know how to come back. And this is even the functional chapter. Once you make a function call, you go somewhere else, right? Remember, I love Mike's talked about, in BASIC. I learned in BASIC also. When you do a goto, you got to be able to go back. There's a go sub. So how do you return back to where? Somebody's got to keep track of where you were. And if you have A calls B, calls C, calls D, there's a lot of stuff to remember how to come back. And all that is taken care of by the system. Well, if you use iteration to do this, and this is in this turtle graphics example, you have to manually manage the how to go back. And so we do this in this way by kind of having a list of things I got to do. And every time you get to the end of one of the forks, you got to queue up. You got to remember 2 more things. Like, well, I better make a tree on the left and a tree on the right. And so all this ugly code on the left is the code that has to do the thing that recursion does for free. So there are a lot of cases like this where the amount of code, and I can't imagine anybody wanting to have the code on the left versus the code on the right for readability, for manageability, for handing it off to your other teammate. There might be some issues that we're going to talk about in a moment about the stack might be overwhelmed, and that's the invention of the one on the left. And also, you can kind of pause it and restart it because remember, the computer is keeping track of the frames, the stack, the kind of where you were. And if you crash, you lose it. But if you were kind of doing it on the left and remembering it, writing to a file, you can restart this. Next slide. So, TLDR, as you're a teacher thinking about how to teach this and balance this, the most important thing you can tell all your students, and you should know yourself and write this on the wall, is any problem can be solved using either repetition, i.e. iteration, or recursion. That's the fundamental thing that you got to make sure that your students walk away knowing. You probably are going to, for most of the problems, choose iteration. You've got issues of the stack frames, which may overwhelm if you just kind of have a loop that's really long and the recursive thing is going to go really long. That's an issue. If you ever try to write Fibonacci recursively, you can't even do more than 30. It's a little ridiculous. I can write down, my daughter, when she was in 4th grade, wrote down all the Fibonacci's of 30 just by doing one after the other, using a little pattern. Well, the next number is the sum of the previous 2 numbers. She got to 30, and I showed her that her computer couldn't even do up to 30. So there's also an issue of speed. But that's not maybe the most important thing to consider. The one you want to think about recursion first is if you've got a recursive data structure like a tree or some kind of recursive structure, like even a linked list can be done recursively, even cleaner. Often they're more elegant, as I showed you the code before. Some programs are screaming to be done recursion. And even stepping back, as Josh pointed out, even better, let somebody else worry about it. I love the idea. It's not my job, man, which is let somebody else, Freddie Prinze, let somebody else do the work. And that's the idea of higher order functions. However, and by the way, however they wrote it is however they wrote it, but you don't have to worry about it. You just call reduce, which is really beautiful. At the end of the day, you got to decide what the purpose of your code is. Is it for tutorials? Is it for speed? Is he running a graphics thing? Is it for the GPU? And think about what the right kind of tool is for that. And as you're thinking about this, Josh and I came up with an analogy, which is, you can put, if salt is iteration and sugar is recursion, you can put both of those things on any food you've got, but kind of food will taste better if you pick the right one. And we were thinking about what's the analogy for higher order functions and what works both, well on food that needs salt or food that needs sugar. And if you deep fry, who is my friends from the South? If you deep fry food, I've had the most delicious deep fried ice cream and deep fried salty stuff, and they're amazing. So higher order functions are the deep frying of the analogy, and decide what you want to do. Thank you very much. My name is Dan Garcia, and I approve this message.